Hi, I'm Alan Ta, and this is an introduction to first-order circuits. So to begin, what is a first-order circuit? A first-order circuit is a circuit that contains only one energy storage element, be a capacitor or an inductor, and that can therefore be described using only a first-order differential equation. There are two possible types of first-order circuits: an RC circuit formed by a resistor and a capacitor, and an RL circuit formed by a resistor and an inductor. In order to solve a first-order circuit, you must first have a step voltage and current source, which the output voltage and current can be modeled by the following formula. The response x of t is equal to x of infinity plus the quantity x of 0 minus x of infinity times e to the negative t over tau, where x of 0 is the circuit response at time t equals 0, and x of infinity is the circuit response at time t equals infinity, which is determined by the component responses over time. Tau represents the time constant, defined as the time required to reach 63% of the final steady response value. For an RC circuit, tau is R times C, and for an RL circuit, tau is L over R. So take this following example of an RC circuit with an input voltage of E and a switch that is open up until t equals 0, and at that time it closes. Using the mentioned equations from previous slides, the response of the RC circuit can be modeled by this following equation. Vc, the voltage across the capacitor over time, is equal to E times the quantity 1 minus E to the negative t over RC for time t greater than 0. Using the former equation, where the response that we're looking for is the voltage across the capacitor, Vc of infinity is equal to E, Vc of 0 is equal to 0, and the time constant tau equals RC. It's also possible to plot the response over time. For example, for that circuit, the voltage across the capacitor can be plotted with this following graph. Notice that tau represents where 63% of the final response is reached. So all in all, there is a 4-step process to solving first-order circuits. Step 1, for time t less than 0, determine the initial conditions. So for your responses of interest, that would be the voltage across the capacitor or the current across the inductor. Remember that these two values cannot change instantaneously, so their values from before 0 are also equal to their values for right after 0. Step 2, for all times t greater than 0, make sure to zero out all independent sources and simplify the circuit to find the equivalent resistance and or equivalent capacitance and inductance. Finally, find the time constant tau. Step 3, determine the conditions of interest, whether that be the value of the voltage across the capacitor at infinity or the current across the inductor at time infinity. And step 4, write the final solution according to that equation. So using this 4-step process, I'm going to turn it over to Lucas, who will be explaining a problem of his design.
Hi everybody, my name is Lucas Barty and I'll be taking care of the example portion of this video. Now, as we can see here, we have a simple RC circuit with a 3-volt voltage source, a 1 kilo ohm resistor, a 2 kilo ohm resistor, and a 3 nanofarad capacitor. And on this side, I have here our basic equations for a star, which you should always just write down. We got these from the rules mentioned in the first part of the video. You should always write these down to get the extra points. And our problem here is find Vc, which is voltage across a capacitor, for all time t. Everything has been in this state for a long time. Now, the first step to solving this problem is, of course, going to be finding our initial condition, which is where this rule comes in. It basically functions with the limits. So, and to find these, we need to look at the circuit when t is less than 0. Now, this is where the it's been at this state for a long time comes in. It simply tells us that the capacitor is acting in a DC situation. It's done charging, which means it's not a capacitor. It actually functions as an open wire. And so that means no current is going to be going through it. So to find Vc of 0 minus, what we actually need to do is we need to find the voltage in this resistor, because these two are in parallel. And if you're curious why, we can actually just find this voltage for an open circuit? Well, just think of the first video where we looked at ideal voltage source, and that's meant to be a resistor, where we base, or not ideal voltage for, but ideal voltmeters, where they have an infinite resistance or zero current, so they have no effect on our circuit, which is basically what's happening here. There is zero current, so these can function as a plug-in point for our ideal voltmeter. And they're in parallel, so the voltage will be the same. Now, the way we would figure this out is, this is essentially a series circuit, because we can ignore any power going through here because there's no current, so it's a series circuit. So we could just do a basic voltage divider. And if you remember, that's also a first video thing, and if you remember, a voltage divider is going to be, so Vc of 0 minus is going to equal the resistor of interest plus the total resistance times the total voltage. When we plug in the calculator to simplify this, this will come out to 2 volts, which will equal Vc 0 minus equal Vc 0 plus. And this is what will give us the first part of this equation here. Now we need to find the second bit, that Vc infinity at time infinity. And the way we do that is we go when t is greater than 0, which yields us a circuit that looks like this, or any such similar circuit which is easier for you to interpret. And it's just the way you look at it. And of course there there's just one node here, so all of these are in parallel, which will be important when it comes to finding tau. So now at this current point we have disconnected the voltage source because the switch is flipped, which means the voltage source is no longer part of the circuit, and now the only thing providing power to the circuit is our capacitor, because he's the only thing that's been charged. Which means our capacitor is going to discharge over time, and in this case it'll happen rather quickly, and then it'll be empty. And since it's the only voltage source and it'll eventually empty, that means Vc as infinity, so it approaches infinity, is going to equal 0 volts. And that gives us this second part of our equation. Now here we can also solve for tau, which again is just Req times Ceq. And now we could see that in this case the 1 kilo ohm resistor is in parallel with the 2 kilo ohm resistor, which if you do the math, is we're going to have an Req of 2 over 3 kilo ohms, and then we can multiply that simply by 3 nanofarads, do a little bit of math with the calculator to deal with the nano and the kilo, and that'll give us a tau equal to 0.002. And now we are ready to essentially solve in, not quite yet get our final equation, but we're pretty close. And that means in this case after t equals 0, the Vc of t is going to equal, so this is our Vc of infinity, which is 0, plus, and then all multiplied, 2 volts for our Vc 0 plus, minus 0 for Vc infinity, times e to the negative t over 0.002, which this could be right into negative 500t, just for simplification. So this is v of t greater than 0, but this isn't the answer quite yet. Now, this is where the last bit, we need to solve for all time t, which means we also need to solve it for t is less than 0, which is basically very simple, where Vc of t is simply going to be a piecewise function, combining our Vc 0 minus, which is our 2 volts when t is less than 0, and then our equation, which is 2 volts e to the negative 500 t, which is when you simplify this above equation, when t is greater than or equal to 0. And the equal to could be arbitrary, it just cannot be the same because it's a function, and that is everything. This is our final answer.